everybody's doing okay with the home isolation. It's not too boring, and you're still keeping in touch with your teammates, and it's not only good for your project, it's also good for you to stay in touch with people. So we were talking about faster path search algorithms last lecture. Just to remind you, the last thing we talked about was A-star search. Okay, so A-star search explores in a more efficient way than Dijkstra, tends to explore towards the destination. So that's what I'm showing there. Okay, and we were talking about, okay, what can we use as our heuristic to allow us to search more efficiently, do what's called a best first or A-star search. And the way we're doing this, we talked about if we simply said we'll never search in the wrong direction, that might be too limiting. We might never get by obstacles like the 401. So we want to do more than that. And what we're going to do instead is we're going to incorporate a heuristic into our sorting of the wavefront so that we don't reject possible solutions if they're going the wrong direction. We just think they're less interesting. We'll get to them eventually, but not right now. So we're going to sort the wavefront by our estimate of, is this the most interesting partial solution to look at? So we got some ideas at the end of last lecture from various people about, well, how could we do that? And I'm showing here this example, just to remind you of what's on our wavefront. So we started at a source, we're going to a destination, and we've been searching for a while. On our wavefront, we have 2 nodes that we're interested in, N2 here, and N1 there. And if we use Dijkstra's algorithm, the next node we'd look at, the next thing we'd pull off the wavefront would be N1, because it has a smaller travel time. And Dijkstra's algorithm just sorts by travel time, or what we're calling best time here. But we can see that N2 is actually probably the smarter place to keep exploring from. It's got a little bit higher travel time of 45 seconds from the source to where we are now, but it's a lot closer to our destination. So it's probably going to get us there in less time. Probably we're wasting our time if we're exploring way out here. So we talked about what are heuristics that we could use, or guesses that would guide us to look at N2 first. And people came up with the ideas, various ideas, like we shouldn't ignore the travel time that has happened so far, so we should take best time into account somehow. Okay, so our sorting function should be something like best time should be part of it, but we should include something that guides us to look at N2 first. So maybe we should look at the distance to the destination, which we can compute quickly because we know we're inside a graph that represents a city, so we can get the positions of everything. And people came up with various ideas of how we could do that. Maybe we could multiply the geometric distance. Okay, so we've got some estimate of distance here. Maybe we could multiply that distance by the best time. Maybe we could multiply it by some constant and add it to best time. And all those things are reasonable ideas, but they're going to be pretty hard to tune. And we really want this sorting to work well. So here's what, well, how about this? Take 30 seconds and think about this. And then I want you to jump in if you've got any ideas of how we could combine this heuristic, this distance, with best time to produce a good sorting function. And we want that to make us look at N2 first, but we also want to make sure that if it turns out there's a big barrier here, say there's a highway, and that our estimate of, it turns out that N2 has to really do a lot of detouring later on, and it's going to get a delay of 90 seconds from where it is right now. And N1 is actually right by an on-ramp to the freeway, and it's actually going to take only 80 seconds to get there. We want to actually make sure that we still find the best path. So we want to have some way to get an estimate of something that we can include with best time, maybe add to best time so we can sort our wavefront well. We also need to make sure that that estimate is dangerous for that estimate to be to predict, so that we would not look at N1 if it eventually turns out to be the best answer. So in other words, as we go through these partial solutions, if it turns out that our estimate was wrong, eventually we should actually go back and look at N1. All right, so does anybody have any ideas of what would be a good estimate to do that? The things that we've talked about before, ideas of multiply by distance, maybe add distance with some constant, they don't quite meet these constraints of making sure we look at N2 first if we had a low estimate of time. So let's say right now we estimate that the time to get there is going to be, well, maybe giving you too many hints. Any ideas of what we could do for our sorting function? So if you got an idea, just unmute and jump in. Otherwise, I'm going to Abid. So, Abid, do you see anybody jumping in?
No, so far none.
All right. So, Abid, what would you do? So we have this constraint. We want to look at N2 first. So we need something that we're going to incorporate into our sorting function to make us look at N2 first. If we think that it's got a low travel time to the destination, so it's close. But we also want to make sure that if we're way off with our estimate, there's a big freeway in the way, and it turns out as we explore other nodes that the delay is getting really high, that eventually we'll look at N1. So what would you do?
Should I give the answer?
You can give me a reasonable answer, sure.
Maximum speed?
Well, I guess basically an estimate of the travel time, right? Is that what you're saying?
Yeah.
Okay, so plus travel time estimate. Okay, so if we take our best time and we add the estimated travel time from where we are, we actually sort the wavefront in a very logical way. If we think that the travel time from N2 is say only 30 seconds, then we think that the travel time from N1, because it's further away, is say 60 seconds, then best time plus our 30 seconds would be 75 seconds for N2, and we'll sort it to be smaller. It'll come out first, we'll look at it first. Whereas best time plus the estimated travel time on N1 would be 100 seconds, won't look at it right away. But if we find that we're wrong, you know, as we go on to other nodes, what's going to happen is this best time is going to increase. So we go on to a node N3, for example. So let me erase a little bit of this. So we go on to a node N3 next. So we take N2 off the wavefront. We find N3 is one of its neighbors. We find that we can get to N3 with a total time of 55 seconds. And we still estimate that the travel time is good to the destination. It's maybe 20 seconds. So then we'd estimate our total time is 75 seconds, still better than the 100 seconds we have over here. We would look at that node next, and we'd keep going. Okay, and as long as there's no blockage, we'd actually keep going pretty much straight to the destination, which is exactly what we want. If there was a big highway in the way, though, so that it turns out we had to detour far around that highway, so we go to an N4 and an N5 and so on up here, and our time keeps going up because we're going further and further, and at a certain point we've actually gotten to a travel time of 100 seconds, and we still think that there's another 25 seconds estimated time to get to the destination. That's not looking so good. That basically says this node that we're at, maybe N8 by then, is not such a good choice, and maybe we need to go back and look at N1. And N1 actually has a best time plus our estimated time of 100 seconds. We would actually go back, take that off the wavefront, we'd look at it. So we'd start exploring from it because this has turned into such a disaster. So in order for that to happen, so this is basically a good sorting function. It has the same units. Best time is the known time back from the source to where I am now. And we have an estimate of how much time is going to occur in the future. If we add those two things together, they have the same units, and it's a logical thing to sort on. But I guess I've given you another constraint that you've got to be careful. If we estimated a low travel time, and or we estimated a high travel time at some point. Well, let me give you another example. Let's say that, let me erase all this, and let's say N2, we estimate the travel time is 30 seconds, okay? So that looks pretty good. Actually, let me change that. Let's say we estimate the travel time is 50 seconds from N2. So we think our total time is going to be 95 seconds. And let's say that we estimated the travel time from N1 was 60 seconds, so our total time would be 100. And let's say that it turns out that we were basically right with our estimate. So we actually follow along a bunch of nodes, and the best time keeps going up, but the estimated future time keeps going down, and we just follow up. We keep pulling them off the wavefront. We go pretty directly to the destination. That's all good, except for the case of, let's say that this 60-second estimate that we had here for the future time from N1 to the destination was too high. Let's say we were right by a highway, and it turns out that we could actually get there in 50 seconds. We will never explore that solution because we're only going to look at the things that are earlier in the wavefront, sorted to be lower numbers. And this solution we've said is quite bad. It has a best time plus an estimated future time of 100 seconds, and that's worse than 95 seconds we estimate for N2. And it turns out to be worse than all the things that we estimate as we go along, because it turns out that we're finding a pretty direct path. So we would never actually go back and look at this, but there was actually a better path starting at N1. We want you to get the shortest path, so this actually isn't good enough. You can't be this targeted. So does anybody then have an idea of what we want for this travel time estimate? Okay, so we want to estimate our future travel time. We want to do that fast. Do we want it, can it underestimate? Can it overestimate? Does it have to be perfect? Anybody on the line have any ideas? So in general, we're not going to be able to make it perfect, right? If we could perfectly estimate it, then, well, we don't really need a search algorithm. So we're not going to get it perfect. So if we can't get this estimate perfect, do we want it to overestimate or underestimate when we have an error? Because errors are going to be unavoidable. So Abid, please tell me somebody's jumping in.
Yeah, so Ahmed says you have to make sure that it doesn't overestimate.
That's exactly right. Okay, and actually, Abid, are you able to unmute, or am I the only one who can do that?
No, you are the only one who can do that.
Okay, that's unfortunate. All right, so that's exactly right. So it's important that this travel time estimate, which is like the future time, must not overestimate. Okay, so it has to be a lower bound. You would like it to be as accurate as possible, because the more accurate it is, the more directed your search is. It will go towards the destination. It will not look at things that are less interesting in the wrong direction. But if you overestimate, it becomes too targeted. It can neglect solutions that actually are better. Let's say, let me see if I can figure out how to bring the participants back in here so I can actually turn somebody on. Let's say I just said, then I'll make this estimate of the future time 0. Okay, because that's for sure not going to overestimate. I'll just estimate all future times as 0. What do I get if I do that? So see if anybody, we actually know what that algorithm is if we just estimate all the future times are 0.
It turns into Dijkstra, Ahmed says.
Okay, so Abid, I'm going to unmute you. Why don't you say it?
So Ahmed said it turns into Dijkstra.
Right. Okay, so very good. So let me mute you again. And okay, so yeah, it goes back to Dijkstra. So we could do that. It's not a bad algorithm, but it's not as fast as A*. All right. So any questions on that? So this heuristic has to be fast to compute, because otherwise we're going to slow our algorithm down. Generally means you need to know something about the graph. And we do know something about the graph. We actually know where all these nodes are. You want to get an estimate that you can actually add into what you're optimizing. So we're optimizing time, so we really want an estimate of time. And it's important that it does not overestimate, because if it overestimates, we can't guarantee you the best path. So you want the best estimate you can get without overestimating. You want it to be fast. Okay, so those are your hints for it. Any questions on that? Okay, so that sounds, I don't see.
Kelly is asking, does that mean we have to find the maximum speed limit of the city?
That would be a good way to do it. Okay, so if you knew the maximum speed limit of the city, then given that you can quickly find the distance between things, that's guaranteed, not to overpredict. So that's a very reasonable thing to do. So that's a good idea. Any other questions? Okay. I'm going to give you a little hint on, so I'm not going to go through all the details of A-star though. So that is enough that you should be able to build it. It's actually not very much code. A-star is mostly about thinking, not very much about changing code, because it's just changing the sorting on the wavefront. There's something that I often see students get confused about is with A-star, the only thing you want to change is the wavefront sorting. You are not changing what I'm calling best time, which is the best time you ever found from a node or to a node from the source, like your start point. We want that to be accurate. The reason we want that to be accurate is we're using that to determine when do we actually allow a new path to explore that node, and when do we say this new path that came off the wavefront is inferior, just throw it away. We want that to be accurate. It should not incorporate some kind of guesswork. So it shouldn't incorporate a heuristic. So what that means is your wavefront, the data element that you put on it, keeps getting a little more complicated. So we already had some way to identify what node did we just put on the wavefront. We had some way to identify what is the edge that we use to get there, so that we can actually backtrace and find the path in the end. We are storing the travel time that is essentially the known travel time that we've used to get to this node. That's so we can see if we found a better path to this node than we had before, when we compared this travel time to the best time that was on the node. And we've now added one more data element, which is just something that we're sorting on. So as you just saw, a good thing that you can use to sort on would be the total known time, the best time or travel time to this node, and a guess of the travel time for the future. But don't get confused and think that just because you have this new number that you can sort on, that you should now call that your actual travel time. It is a guess of the total past plus future travel time that goes through this node. You don't want to use that when you take something off the wavefront and you're doing that check to see, is this a better path to a node, to this particular node than I had before? Does that make sense? So Abid, any questions that you can see in the chat?
None.
All right, let's see if I can go and change my share to demonstrate what the A-star looks like. Yeah, let's see, this should be, I'll just share my whole screen. We'll see what happens when I do that. Whoops. Okay, I don't want to do that. All right, let's try it a different way. Let's do VNC Viewer again. Okay, Abid, can you see the VNC Viewer screen now?
Yes.
Okay, let me show you the difference between A-star and Dijkstra's algorithm visually. And these graphics are courtesy of Abid, who's been busily coding them up. Okay, so let's look at Dijkstra's algorithm. So I want to go from the center of Toronto out to the edge, and hopefully that animation was visible. What do you think, Abid? Can you see it?
Yeah.
All right, so you can see it kind of expands in all, it's pretty efficient, but it expands in all directions. So it's going backwards, forwards, etc. Okay, now let's switch to A-star. Okay, so we go to A-star, it's much more targeted. You notice that it is faster, and it doesn't tend to go in the wrong direction as much. Okay, so that's how A-star looks, and it is more efficient. All right, let's go back and do another share. All right, and it looks like I managed to kill my PowerPoint, so let me bring that back up. All right. Any questions on A star? Okay, in that case, we're going on to the next thing. Okay, so the last pathfinding algorithm you have to code in Milestone 3 is this walking plus driving one. So it's a little more tricky. I recommend you get the driving one only working first, and then you move on to this. Or there are 3 of you, so perhaps you can do it in parallel. But make sure you got people working on the driving before you focus exclusively on this one. Okay, so just to remind you, you've got a starting intersection, you've got an end intersection. Those are given to you, but you need to find
Hey, everyone.
yeah.
I can't see the shared screen.
Okay, let me go back and see what I can do here. Let's see. Let's see that you are on here. So let me try the share screen again. Can you see it now?
Yes, right now I can see.
Okay. Let's bring it back up. Thanks. And let me try to get this back into full screen mode. That is interesting. Okay, can you see that now?
Yes.
Okay.
Right now we are seeing the. Wait.
You see that?
Yeah, I can see it now.
Okay. Okay, so you're given a start intersection, you're given an end intersection, and you have a walking time limit and a walking speed. So you've actually got a lot of kind of intermediate intersections, which I'm calling walk intersections. Okay, so we don't tell you what is the intersection you should walk to. We just give you a constraint on it can't take longer than a certain amount of time. Find the walking intersection that you can get to that minimizes your driving time, because you're going to meet an Uber driver and the Uber driver is going to take a few minutes to get there. You want to make use of the time. Okay. So we have already finished the first pathfinding algorithm. Okay, so that's called find path. It goes from one intersection to another intersection. And so we can build on that. So maybe how about take 30 seconds. It's kind of hard for you to do in your teams, but think about how could we build on that function and solve this more difficult problem. And just think about ways we could use it in relatively straightforward ways. The way we write the tests for these milestones is first we test, do you have something that functions? So you actually want to get something working. Then we test, is it fast? So we have increasingly difficult speed tests. So let's just come up with any technique, given that you've got this pathfinding algorithm written between 2 intersections, so that you could solve this more difficult problem. Don't worry too much about whether it's going to be fast or not. Then we'll try to see if we can come up with ideas to speed it up. Okay, so I'm just going to leave you a few seconds while I mess around with the participant view, and then I'll call on, we'll see if anybody is brave enough to jump in with an idea. All right, so if you want to be the brave person who gives an idea, just put up your hand or unmute yourself. I can't actually see the chat. So Abbott, are you seeing anybody in the chat coming up with ideas?
No one answered anything.
Okay, so your 30 seconds are up. For the honor of the class, is anybody brave enough to jump in and say, look, there's a way we can do this that's relatively straightforward. So don't worry about speed. You got this fine path. What are you going to do?
So Annie is saying, can we use the function to find the nearest intersection, then just do the find path from there?
Okay, so do you want to find one intersection, or do you want to do this for multiple intersections? You can unmute her. What's the name?
Ani, A-N-I.
Okay, let's see.
So I know in Milestone wrote a function that would find the closest intersection to a point.
Mm-hmm.
So we could use that to then find the nearest intersection and then do the car version of the find path from there.
So that makes sense. Okay, so we can take an intersection and we can use the car driving time function to find the path from it. And you're saying take the closest intersection to where we are. Now we do give you a start intersection, so that closest function is going to tell you the closest one is the one you're standing at. Do you want to ask it about some other intersections too?
I think I might be confused. So you're giving us just an X and Y coordinate on the map, right? Like a lat one?
We actually give you a starting intersection where you're standing, right?
Okay.
So we give you a start intersection. Okay. Oops, let me go back. I'm going forward instead. Let's see if I can go backwards here. Yeah, we give you the starting intersection, but you need to figure out, you basically need to figure out what is an intersection you can walk to and then the driving path from it. And we don't want just any random intersection you can walk to. We want you to find the one that's going to minimize the driving time, but you can still get to it within our time limit of walking. Like you're willing to walk 5 minutes, but not any longer. Does that make sense?
Yash is saying to expand on what on that, we could look for the intersections that are in the direction of travel only.
So you could do that. So you could look at, so basically we can look at, let me get rid of this window because I think this is messing me up. Okay, so try multiple walk intersections. And for each one, you can basically use this find path function that we've already written from walk intersection to the end intersection, okay? And then take the smallest. So we can do something like the time is equal to that, and then take smallest time. Find that path. So yeah, we could invoke our driving path function multiple times from various ideas of starting like walk intersections that we could walk to. And you're right, a good heuristic could be, well, look at the walking intersections that are in the right direction and that are, not too far away. So those are good ideas. So let me go on and build on that. So here's my brute force one. So I've got a simpler algorithm still. And what I'm saying is I'm just going to go through all intersections. I'm going to define a variable called inter, which is the intersection I'm looking at right now, but I'm going to go through all n of them. So I'm going to say my walk intersection is equal to this intersection. And then I'm going to say just call my find path function, but use walking time limits instead of driving time limits. So I had to update my find path function a little bit to do that. And I want to go from my start intersection to this walk intersection. And this walk intersection is just, I'm going to go through every possible walk intersection. So this is going to be first intersection 0, then I'm going to do this again with intersection 1 and so on. So I find a path. Once I find that path, I can check, is it within my time limit? Okay, because I've been told in this function call, there's a certain limit of how long the person will walk for. If it is, then I call my find path function I just wrote to say, tell me the driving time from this walking intersection to the ending intersection. Check how long that time is. If it's better than the best drive path I've seen so far, then update my solution. And when I'm done, at this point, I have the best. Okay? So anybody disagree that this will get me the best solution? Okay, so I don't hear anybody unmuting, so I'm going to take that as agreement that you think it's going to get the best solution. So here's my question. What is the computational complexity of this? And this will get the best solution. Okay, so if you want to get a legal and actually optimal, so shortest driving time path, this will work. And this will pass a bunch of our tests. But it's not going to pass the speed tests. And the reason why is the complexity. So does anybody want to weigh in with what they think the complexity of this is? And remember, we have n intersections in a city. So that's one of the numbers you're going to need. And the other thing is that both Dijkstra's algorithm and A star, which are the two best path search algorithms we've found, are n log n complexity. Okay, they look at every intersection in a city in the worst case, and they do a sort on those intersections in the wavefront. So that sorting is log n. So they're n log n for this find path. Oops, let me go forward again here. So this find path is going to be n log n if you've used Dijkstra's or A star, which you should use. And then the number of intersections in a city is n. So what's the complexity of this overall algorithm? Anybody want to take a shot at it? And let's see if I can see what the participants are doing. Abid, you see anybody who's willing to weigh in?
Gyu Huang said O of n, but I'm following up with him.
Okay, so O, is that the total complexity? So there's an.
That's what I understood. I'm not sure if that's.
Okay, I've got Ani's. I'm unmuting you, Ani, because I can see you've got your hand up. So, what do you think? Oh, I think I made Annie drop off the phone. So, okay, so anybody want to take a shot at this one?
So Yash is saying n squared log n.
Sorry, can you say that again?
Yash is saying n squared log n.
Yeah, so it's n squared log n. So let me shrink this down. So basically, we're going to go through this loop n times. So for every possible walking intersection, we're going to call find path, which is going this find walking path, which we're going to use Dijkstra's or A star algorithms for that. So that's n log n. And then if it passes that test, it's close enough in walking time, we're going to call this drive path, which is n log n. So we're going to do n log n plus n log, sometimes n log n work, but that doesn't matter. That's just n log n in the inner loop then. And we're going to do that n times. So this is going to be n squared log n. When we have cities with 100,000 to 1 million as n, this is big, okay? Anything that has an n squared in it should make you really scared. So this is going to give you problems. How can we make it faster? So we already heard some ideas of, well, maybe just don't look at all the walking intersections. That seems kind of crazy. You're looking at every single intersection in the city. So we had ideas of, well, maybe you could just look at the ones that are in the right direction, etc. Any simple ideas that are guaranteed to not get rid of the best solution, because you still want to get the best solution, but can cut the time of this. So what do you think? So let me see if anybody is weighing in here. What do you think, Abid? Do you see anybody?
No.
Okay, so do we really have
So
to?
Jeremy is saying only the intersections walkable within the time limit.
Yep. But that's what we're doing. We are checking that here, but we're checking it by actually invoking this pathfinding algorithm. So this find walking path is checking, are you within the time limit? So I think, Jeremy, are you saying that we don't really need to use that find walking path all the time, like on every single intersection? I think that's what you're saying, but how will you avoid calling it all the time? It's the right idea. So what do you think? Oops. So Abid, is Jeremy saying anything else, or you want to?
No.
Okay. So I don't want to unmute people without them being willing participants. So we don't really need to call this find walking path all the time. Let's say that I've been given 5 minutes to walk to some intersection. I'm willing to walk 5 minutes to meet an Uber. Do I need to check an intersection in Richmond Hill to see if I can walk there by actually running Dijkstra's algorithm or A star algorithm? Like, no. I can check geometric distance. I can see that geometrically that is 20 kilometers away, and I can only walk maybe 1 kilometer every 10 minutes, and there's no way I'm going to get there. I don't need to go and check through all the intermeeting intersections. I don't need to use Dijkstra's algorithm. I can just say, if I was able to fly over all the buildings and go straight there, it's 20 kilometers away, and I can only walk 1 kilometer every 10 minutes. So that is going to take me, something like 3.5 hours. So I don't have to call find walking path. That code to check, is this walkable was order 1. Okay, so I can do an order 1 check by distance. Okay, and walk speed. If I did that, then I'm not going to need to call find walking path nearly as many times. I only have to call it for things that are actually close, that have some chance. Say there are k of those. And for each of those, I'm going to call my driving find path. But if I do that, I've cut the complexity quite a bit. It's now k times n log n. And k is basically the number of intersections that are reasonable possibilities. Does that make sense? Reasonable possibilities where I've quickly checked using geometric distance. Okay, so that's a pretty simple change. I've not written the pseudocode, but that's the idea. So k log n, whoops, with essentially pruning. I'm immediately throwing away with a quick check the walk intersections that make no sense to do detailed checks on. All right, okay, can we do better than this? And I'm going to motivate this with a quick picture. Let's look at Dijkstra's algorithm. So you take Dijkstra's algorithm and starting from a certain source, it basically expands this wavefront outwards, finding the minimum travel time to all those nodes. And eventually we hit some destination. And then we basically say, let's backtrace, we found a path. Okay, so that's how your find path algorithm is going to work if you use Dijkstra's algorithm. Works slightly differently if you use A*, but same basic idea. When we reach this destination, we actually know a lot more than just the minimum travel time to that destination. We actually know the minimum travel time to every single node in these circles. Okay, so Dijkstra's algorithm can find not just one travel time to one specific destination, even though that's how we used it for our original find path in Milestone 3, the driving path. It's finding a lot more. It actually knows the minimum travel time to all of the nodes in these circles. Okay, so can we use that? And I'm just going to flip through this. That animation doesn't really show you much more. It's basically, we can find the paths to a bunch of destinations at once. So let's build on that. That means we can use Dijkstra's algorithm to find all of the destinations that we can walk to quite efficiently. And n log n times. So n intersections in the city, run Dijkstra's algorithm once, and it'll actually find the minimum travel time, which could be walk time if we use the right travel function, in n log n. And again, let's say that k of those are actually within our walking time limit, okay? If we take only those k intersections and we ran an A* find path from each, now what is our complexity? So this is actually a relatively tricky question. Does anybody want to weigh in on this one? Okay, so I don't see anybody, but basically we've done n log n work and we found all of our possible walk intersections. There are k of them. For each one of those k walk intersections, we could invoke our A* algorithm. And A* algorithm is again k is n log n. So our complexity is actually still k times n log n. So it hasn't actually gotten a whole lot better than it was when we were just using our simple pruning function to avoid calling A* a lot of times on to find the walkable intersections. So this will be faster, but we still haven't changed the overall complexity of our algorithm. Can we do better still? Any ideas on how we can do better still? Oops. Let me get rid of that. What do you think, Abbott? Anybody weighing in?
No, but there is someone unmuted. I can't find him.
So if someone is unmuted and wants to stay unmuted and wants to be unmuted, speak up. Okay. It might be you actually. So
No, I was muted, but I'm not sure. Anyway.
okay, so last chance. I'm going to give you a tip if you don't go for it. Let's see if I can get this back again. Okay, so can we do better still? Yeah, you can. The basic idea is, again, think about what your pathfinding algorithm is doing. We can use Dijkstra's algorithm, as I just told you, to find not just one path, but many paths to basically paths to all of the nodes that are within some travel time. Your wavefront, so far, you've been starting with a single node, right? It's always been the starting intersection, and that's what you put in your wavefront to begin. Okay, so we can start the wavefront instead of with one node, one possible source. We can start it with all k walkable intersections. I think I've been using the term walk intersection. So again, your code doesn't change very much, but you just change how you think about the algorithm. Instead of saying I start here, you say these are all possible starting points. What should I use as the travel time for those k intersections? So it's no longer just one intersection. I'm going to start the wavefront off with a whole bunch of intersections, all the ones that I could walk to in the walking time limit. What should I use as their travel time? Again, I'm trying to find the minimum driving time. So what should I put them into when I'm trying to find the driving path, and it could start at any one of those walk intersection possibilities, what should I put them into the wavefront with? So any thoughts on that? Okay, whenever I put something in a wavefront, I have to put the node in the wavefront, but I also have to say, what is its travel time? What do you think its travel time should be? So anybody on the phone want to take a shot at this? Okay, so I'm going to leave that as an exercise for you guys to figure out that. And you can email me if you want, or if somebody now wants to take a shot at it. If someone takes a shot at it, I'll tell you if you get it right or not. But otherwise, I'll leave that as an exercise for you guys to figure out. So last chance. All right.
There are several answers, but I'm not sure which one is. So Annie is saying segment length over walking speed.
For those, this is when I'm now taking that's correct. When I was doing the Dijkstra's algorithm to find all my walkable intersections, you should use that as your travel time for passing a certain segment. Now that I've found those walk intersections, though, I found all the possibilities. I'm doing another search. Okay, so I've started the search again. Now I'm using all driving times because I'm just trying to find the minimum driving path, but I'm saying it could start at any one of these intersections that are possible that I could walk to. So when I start that search, what should I put those possible intersections, those nodes, into the wavefront? What should be the travel time I use for them? Essentially their driving time, right? Like this is their starting driving time. So any other thoughts?
So Helen said the driving time, and Jordan said, is it 0?
So 0 is exactly right. So you start them with 0 because that is their driving time. You walked there. And the way we have phrased this problem, as long as you can get there within the walking time limit, you get there before the car. So it's all free. The car arrives, you get in, that's t equals 0. And that means that if you're trying to search for the best driving path and you want to search at the same time for the best driving path with any of these intersections being a possibility, you can put them all into the wavefront with a travel time, a driving time of 0. And now Dijkstra's algorithm or an A-star algorithm will basically search all the paths emanating out from that whole group of intersections, and it'll do that more efficiently than if you just said, let's start from this one walkable intersection first and do a driving path search, and then let's do this other one second, and so on. So you can put them all together in the wavefront, and the travel time is 0. You should start for that. Does that make sense? Abid, what do you think?
Yes, for me it makes sense.
So if I've confused you, then we're really in trouble. But on the chat, it looks fine.
Yeah.
Okay. Any last questions on the chat?
So Kelly is saying, if time only starts when we get in car, do we only care about intersections on the max limit of our walking time?
That's a good point.
But I don't think so.
I mean, it's hard for you to guarantee that. Like,
Yeah.
basically, there are lots of weird cases. There are one-way streets. There are freeways. So could there be an intersection that's kind of not on the boundary of that circle that might be a little faster? When you consider one-ways and the complexity of street maps, it's possible. In practice,
And probably also one of the intersections inside can be a start of a highway. So taking that highway would take you faster.
yeah. So you're right that the common case is probably that the best starting interface will kind of be on the edge of the region you can walk to, but we can't guarantee it. There are cases where that might not be the case, so it's better not to assume that. And with the algorithm I just laid out, it's fast, and you wouldn't have to assume it.
There are 2 more questions. Scott
Sure.
is asking, so do you reverse the process? And Helen is asking, can you explain again?
Can I explain again? Okay, so basically there are multiple ways to solve this. And actually there are other solutions, and actually some students have come up with actually quite novel solutions that are different than what I've talked about here, but are fast enough, so you don't have to do it this way. My basic algorithm was, well, let's see. So we had the basic algorithm, which was, let's see. I guess all of these algorithms that I'm showing you break into 2 pieces. Find all of the intersections you can walk to within the walking time limit, and then from that whole set of intersections, find the best driving path. And one technique would be use Dijkstra's algorithm or some other algorithm to find those walking intersections, and then invoke your driving path function over and over again from one intersection at a time. But there's a trick. There's a trick is that if you think about how Dijkstra's algorithm and A-star algorithms really work, they don't care if you start from one intersection or if you start from many. So if you know all the possible starting intersections, you can put them all in the wavefront at the same time with the appropriate travel time. And because we're saying that time starts at t equals 0 when you get in the car, that travel time is 0. And then you can just run your regular Dijkstra or A-star to try to get to the destination. Does that make sense? So hopefully that answers Helen's question. Are there any other questions, Abid?
Sorry, I couldn't hear you.
Oh, any other questions, or should I move on? I'm going to take that as I should move on.
Oops. Annie is saying, I didn't understand the 0 thing. The 0 thing.
The 0 is basically when you start your path search for driving, we are saying that we only care about minimizing driving time. So this really breaks into 2 things. Find an intersection you can walk to that minimizes your driving time. So if you can get to an intersection in a certain walking time, it just passes the first test, okay? It's a possible start point. But now when you're trying to find the travel time, you don't count how long it took you to walk there, because the idea is you're meeting an Uber. The Uber's going to come meet you. The Uber's not going to get there for 5 minutes. It doesn't matter if you walk there in 30 seconds or 4.5 minutes or exactly 5 minutes. You are waiting 5 minutes. At the point the car gets there, you get in and you want the minimum travel time to get to your destination. Does that make sense? And that's why we start the travel time at 0. We are not including the walk time in the total, in sort of the optimization function. We're just saying you have to be able to walk there in a certain number of minutes, but you're choosing where to walk to in order to minimize your driving time, because the car's just not going to get there for 5 minutes. So you're trying to make use of the time. Does that make sense?
Yes, that makes sense. And Jose is asking, If we don't check the type of the road, is it fine to walk on highways, or do we need to be more realistic?
No, you can walk on highways. So you're right that in real life, if you go commercialize this afterwards, highway check-in, you might have some litigation problems. But it's too complicated for us, and the spec gets too complicated. So we're just saying walking is fine anywhere. Okay? You're an extremely aggressive pedestrian. You're going to walk anywhere that a car can go. And you can walk the wrong way down wrong ways, one-way streets, and so on. Any other questions?
No.
Okay. So I want to get through, I'm probably going to go a few minutes over, but let me give you a few tips on tuning Milestone 3, and then we'll stop for today. But I'll stay on the line for any questions, and I'll get rid of the slides so I can actually see what's going on. Okay, so performance tuning tests, performance tuning tips. So the hardest part of Milestone 3 is actually making your algorithm fast. Well, you do want to get correct algorithms, but then after that, you want to make them fast. When you tune things for speed, you want to think first about algorithm. If you just have a bad algorithm, it's going to be slow. Then about data structures, and finally about low-level code. So don't worry about your low-level code until you've gone through the first two. And usually, unless you've done something quite weird in your low-level code, you just won't have to worry about it too much. Okay, so when you're debugging algorithms, these algorithms are going to move a lot of data. So they're more complicated than most of the algorithms you've written so far. So start with a very simple test case. And we've written some of those in the unit tests for you. So Abid, I think they're called like simple. Is that correct? Like
Yes.
Cases that have
simple legality and simple optimality. Okay.
So simple legality are basically tests to check, did you find a legal path? Okay, so it is a correct driving path. You didn't go the wrong way down one-way streets. You didn't jump from one part of the city to another without using any streets, etc. And the simple ones are basically really close together. So you want to start with a test case where you're just going from one intersection to one that's right next to it. Okay, because that you can watch in the debugger and you can make sure it works. Then you want to move things. Okay, so we do two things right together. I would actually watch this in the debugger. That's how I check my own code. So I don't just check that it got the right answer. I watch how it got it. Then the next thing I do is try a little bit harder. So instead of adjacent intersections, I'd be 2 intersections away. That's still small enough that I can watch it in the debugger, and if things go wrong, I can figure it out faster. Once I start going across half a city, you know, there's so many nodes that you're going through that debugging it is much harder. So make sure you debug these simple test cases first, and they are literally called simple in the unit tests. Okay, now eventually though you get into the bigger test cases. Now what if they're not doing what you want or the algorithm is slow? It's hard to see large amounts of data in the debugger, so you can use graphics to animate or visualize this. You don't want to use visualization leave visualization on in your final submission. We do disable graphics, so we try to disable it so that it won't cause any problems for the auto tester, but there's always a chance that you did something that doesn't get disabled, and it might slow down your program or cause a problem. So graphics are good to visualize. Turn it off before you submit. Okay, I'm not going to walk through all this code, but this is actually essentially the high-level code that we use to draw, animate the algorithms that we're showing you in class. So we'll include a couple of libraries, we want to be able to turn it off. So being able to turn it off, usually what we do is we'll use these define statements. So we've defined something called visualize, and we can put code that draws our solution inside these what are called compiler guards. So if, def, visualize, end if. So if I comment out this one line, define visualize, then none of this code will get compiled. So it won't cause you any problems for sure in the auto tester. So your visualization code is best to put it in compilation guards like that. Okay, what does the visualization code actually look like? We're basically saying, give me the renderer, the EasyGL renderer, and then we say we're highlighting street segments. So we're just saying draw a street segment, and it's a street segment we're about to explore. So in our animation solutions, every time we're putting something into the wavefront, actually, I think we're taking something out of the wavefront, we draw the street segment that we used to get there. So that's what you're actually seeing. So we just grab this renderer, we draw a street segment, and then we actually say flush drawing. Flush drawing, we're not actually drawing this in callbacks. We're actually in the middle of the algorithm. Graphics libraries, including EasyGL, are allowed to just buffer up graphics for efficiency. They don't have to draw it right away. We're calling this function to say we want you to draw this right away, because we want to see it right now because we're actually animating. And then it turns out this would be so fast we wouldn't see it well, so we delay for 50 milliseconds. And that delay function is written down here. It's just another use of the chrono library that you've already seen. So I'm not going to go through all the details, but this is really it. Like it's not very difficult with EasyGL to actually animate how your algorithm works. You're just not drawing in callbacks. You're instead drawing right inside your algorithm. You're saying flush it, so make it show up right away, and you're delaying for a little while. And it looks cool too. The other thing you can do besides visualizing your algorithm is you can use profiling. And I'm not going to go through how to do that because we talked about it in tutorial 7. If you missed it or you've forgotten, go back and look at the slides. Okay, and I'm not going to go into milestone 4. We'll start talking about that tomorrow. But before, let me go and show you a last demo. So bring up the sharing here. Okay, so okay, so Abid, can you see the map?
Yes.
Okay, that sounds good. Okay, so I already showed you Dijkstra and A star, and let me show you. Okay, so this is actually these graphics are courtesy of Abid. Let me basically go and show you the multi-source Dijkstra. So what I was talking about for the walking path, well, the walk plus drive. Remember, I told you you could use various techniques, with the most efficient one being using Dijkstra's algorithm to find all of the intersections that you can walk to in a certain amount of time. And the Dijkstra's algorithm and A star algorithms, they don't actually have to start from one specific spot or one specific intersection. They can start from multiple ones if you just put multiple possible start points in the wavefront. So that's what this is doing. So I'm putting in multiple start points in the wavefront. Okay, these are really far away, so they're obviously not different walking points, but let's just say these are different spots I can start the search from. And now if I run it, let's see, that was multi-source entry on. So it's good you're on the line, Avid. I did this before, but I think let's try this again. So let me do the multi-source entry on. Okay. There are 3 different sources, and I click on this, right, Avid? Multi-source entry.
Yes, just click on it again and click on any intersection in the city.
All right, I have to click on the destination. Okay,
Yep.
So those are all my possible start points for this multi-source Dijkstra, and I can go over here and say, let's search from there. And in that case, only one of them was kind of an interesting start point, so Dijkstra's algorithm was smart enough to never really look at the other ones much. Let's do one where we go in the middle. Okay, so I'm going to put one out here, one out here, one out here, and let's say I'm trying to get to the middle point. And actually, it's still not middle enough. Let's go here. Let's go there. Okay. Let me try putting this in the middle. All right, and there, hopefully you saw that. The algorithm naturally starts exploring from all of them, and it is sorting the wavefront. So whichever one is getting you to, well, basically it considers all of those start points, and it considers the places you can reach from those start points all together through that wavefront. And the algorithm really hasn't changed much. You're just changing what do you put into the wavefront at the very start. Let's see. So that is all I was going to cover today. Any questions?
When will the recording be posted? Dave is asking.
It should be within about half an hour of this lecture. It basically, I basically just have to click stop recording, and then Zoom will start rendering it. So it usually takes, from what other profs have told me, about 20 minutes or half an hour for it to render, and then I'll post the lecture.
And Andy is asking, if M4 doesn't have graphics component, do we not have to make graphics for it?
Yeah, for M4, you do not have to make graphics. So you can make graphics if you like them and you think it'll be cool for your final presentation slides or help you debug, but you absolutely don't have to make them. I actually finally found where the chat window is too. So no. Okay, so someone is asking, do we have to undo the graphics we did for M2? No. Okay, so do not get confused. I'm not asking you to delete code. Basically, all your graphics for M2 are drawn in callbacks when we call your draw map. Okay, that's fine. In our unit tests for M3, we are not going to call your draw map. We're just going to call your algorithm. So none of those graphics are going to get executed. They're not going to like cost you any time. What I'm saying is but what you can do in M3 if you want, is you can actually call draw map yourself, so that you bring up some graphics. And then inside your algorithm, you can put in code just like what I showed you. Highlight the street segment, highlight an intersection, flush the graphics, delay, and you can see what your algorithm's doing. Now that animation code is actually inside your algorithm, because that's the whole point. You're trying to see what the algorithm's doing. So I'm saying we will turn off graphics. So we'll try to make sure that code, if you put it in, is not active. But because we can't guarantee it, because people do things sometimes in different ways that we don't expect, it's best if you deactivate that code before you submit. But that is drawing code that you chose to write inside your M3 algorithm. If you never write that code, you do not have to deactivate it. Does that make sense? Yeah, so basically I am saying any graphics code you put in your algorithm, it would be safest if you put in those if-def visualize so you can turn it off. If you just go, I don't want to write any graphics code in my algorithm, then you're for sure safe. Okay, it's a nice way to be able to visualize it.